everyone. I wanted to come on and talk to you about our next type of bonding, which is covalent bonding. Okay. And this is different from the type of bonding that we talked about before, which was ionic bonding. Okay. This is the one we just finished. This is the one we're moving to. And the way you can tell the difference between the two is covalent bonding. So step back a second. Remember what ionic bonding was about. It was about transferring electrons around. It wasn't about keeping them or anything like that. It was about getting rid of them or taking them up in order to get a full valence shell of electrons, or 8 out of 8 on the outside. Okay. So with this, we dealt with elements that were one from each side of the periodic table, if you remember. We dealt with one from this side, or like one of the transition metals, and one from over here. In other words, it dealt with one metal and one non-metal. Okay. Or you could say it happened between a cation and an anion. Okay. Covalent bonding is not about transferring anymore. Covalent bonding is actually about keeping the electrons you have, but still being able to get to the number 8 for your outside valence shell. And this involves sharing of electrons. Okay, we're done with transferring. Get rid of that. We're now into sharing is caringville. We're not into the trading aspect. Covalent bonding is all about sharing. Okay, this type of bonding deals exclusively with non-metals only. Okay, and this happens between 2 or more of them. Okay, so ionic bonding, like we said before, was between one from this side and one from that side. In covalent, we're just dealing with nonmetals, which you'll notice is just on my periodic table is the dark green color that's right in here, and then hydrogen as well. So those are the only elements that we concern ourselves with covalent bonding. Okay. So what I'm going to do is I'm going to deal with I'm going to show you how that works if we look at something like, let's say we have a compound such as, let's look at CO2. You guys know that one pretty well, right? So we're going to look at CO2, also known as carbon dioxide. That's the stuff we breathe out of our mouths from our lungs, okay? And it involves carbon and oxygen. So I'm going to make carbon brown and I'm going to make oxygen green. So we're going to go back and we're going to look at using our Lewis dot structures again to make this easy on ourselves. Okay, so write down your symbol for carbon and then write down your symbol for oxygen. I'm going to start with one oxygen for now. Remember, Lewis dot structures is our valence electron. So if we find carbon, it has 4 valence electrons. So 1, 2, 3, 4. Okay. And oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Okay, and I'm going to put the other oxygen over here so that I can save on space. And I'm going to draw it a little bit opposite to this one just to save room and make things make sense, okay? So we have both of our elements that are present and all of our atoms that are present. Notice I said elements and then atoms. So we have 2 elements, but we have 3 atoms because we have 2 oxygen, okay? And what we have to do is, like I said, this is all about sharing electrons. All 3 of these want to get to 8. But right now, none of them are there, are they? This one is at 6, so is this one, and this one is at 4. Right? How can all 3 of these be happy if they're all lacking valence electrons? Well, how many spots does each oxygen need to be happy? So oxygen, if you notice, needs 2 more. And carbon, so each oxygen needs 2. Carbon has a need for 4 more to get to 8. Now, some of you might be thinking, well, carbon can just give up 2 apiece to oxygen, just like it normally would if it were going through an ionic bond. But the thing is, carbon with where it's at is stubborn and doesn't want to lose electrons because it's in between 4 and 8. So it kind of is, it doesn't want to give up those 4. It would rather try and gain 4. But oxygens over here don't want to lose any. They're stubborn too, and they want to hold on to their electrons and gain 2. So what do? What has to happen in this is there has to be some sort of compromise here. Instead of looking to fill these empty slots here, can't we just share what we already have? If oxygen said, hey, carbon, I'll let you borrow this electron as long as you give me access to that one. And then they also make a deal where oxygen will share another electron with carbon, another one of carbon's electrons that are free. If it does this, carbon gains access to 2 more electrons, and oxygen as well gains access to these 2 electrons, which means oxygen now has access to a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay? It's not necessarily, like I said in this case, about having 8 electrons. It's about having access to and being able to share 8 electrons and have access to that. Oxygen at this oxygen at this point is happy. It's content. It has access to all 8 electrons. But then we look at carbon over here and we go, okay, carbon has its 4 and access to 2 more. It has access to 6 out of 8. This carbon is not happy yet. And neither is this oxygen. But, hey, we have 2 extra electrons that carbon can share and 2 extra over here on this oxygen that it can share. So they make the same deal as this oxygen over here to share 2 electrons with each other to give carbon access to the 6, including this, and the 4, the extra 2, which is 6, and then these extra 2, which get it to 8 of 8. Okay? And then this oxygen now has access to 8, just like this oxygen with these 2. 1, 2, 3, 4, 5, 6, 7, 8. If everybody is at 8 of 8, this means that everybody's happy with this arrangement, and this is how the molecule bonds. It bonds like this, so that everybody's happy and has access to 8 electrons in their outer valence shell. Okay? This is why some of these bonds, like covalent bonds, can be kind of tricky. And this is because we can have a multitude of different ways that we can combine certain elements together. Okay? So when we look at this, we see, like, we can tell how many bonds are between each of these, and we can tell the strength of our bonds as well. So if there's one shared pair, that's a single bond. If there's 2 shared pairs, that is a double bond. 3 is a triple bond. 4 is a quadruple bond. So on and so forth up the way until you get to 8. Granted, like things past 4 bonds, things like 5 through 7 shared pairs is like almost unheard of, and these are rare. They do have names for these bonds, but they're very, very rare. So if we look at the bonds between these, we don't count the total number of bonds on an atom. We count the number of bonds between an atom and another atom. So, for example, between this carbon and this oxygen, we have 1 double bond. And then over here, we have another double bond. We do not have a quadruple bond because that would mean we'd have to have 4 shared pairs between 2 elements. And that is not the case here. It is 2 between a carbon and 1 oxygen and carbon and another oxygen. Okay. So yeah. That's the basics behind covalent bonding. I can do more examples in the videos ahead. But just know that it's all based on sharing. It's between nonmetals only, and it's basically to get everyone here that's in it to access to 8. And when we have a certain amount of bonds between 2 atoms, they have a name, and that also talks about the strength of the bond. Your 1 shared pair is fairly weak, whereas things that have bonds between more than 1 are stronger bonds. Okay? All right. I'll do more later, but these are the basics. I'll talk to you guys later, and let me know if you have any questions. Okie dokie. Bye-bye.